So in this video we're going to return to our lab preparation of a liquid organic compound, focusing particularly on the preparation of halogenoalkanes from the corresponding alcohol, and looking in particular at the example of preparing 1-bromobutane. You should by now have watched the introduction video and also the practical video so that you can see this reaction actually taking place. And we're now going to look in detail at the different steps in this reaction and preparation. So just to remind you of the reaction taking place, this is from your notes on page 10. We're preparing a primary halogenoalkane from primary alcohols, the corresponding primary alcohol. And we're doing that by reacting it ultimately with hydrogen bromide. We don't add in hydrogen bromide directly, and we add it in situ. And that means that we put in two other reagents that react together to give hydrogen bromide within the reaction mixture. Those two other reactants are concentrated sulfuric acid and sodium bromide, and they react in a way that we've seen before in our halogens topic. So that's in step 1, where the sodium bromide reacts with the concentrated sulfuric acid to give hydrogen bromide in situ, and also sodium hydrogen sulfate, which doesn't really have anything to do with our preparation. And then step 2 is when our butan-1-ol, our corresponding alcohol, reacts with that hydrogen bromide in situ to produce our 1-bromobutane. So overall, our equation is down here. If you have a look at it, it's our butan-1-ol reacting with sodium bromide and concentrated sulfuric acid. Remember, that is just in order to produce HBr in situ. And that reacts together to give bromobutane and sodium hydrogen sulfate and water. So you should have watched the practical video by now, so that you have an idea of what these steps look like in practice. But we're going to go through step by step and explain why we do each step. So over on page 11, we begin looking more closely at this method of preparation. And as I said in the introduction video, you may not be asked in an exam to recall this method step by step right from the start until the end. But you could be asked for a few steps within it. You might be asked, what would you do next? And you may also be asked in your theory exam or in your practical theory exam why you do certain steps, or what reagent would you use to do the drying step, or that sort of thing. So when we look at this more closely, what we're really doing here is trying to explain to you why we do the steps that we do at each step. Okay. So in general, your steps are in bold, and then in italics it explains why you do that step. So step number 1 is to mix the sodium bromide with butan-1-ol and water in a pear-shaped flask. So over on page 10, we wrote our overall equation for this reaction, and I've written it again on the screen. You could write it at the top of your page or on the left-hand side, as I've done here. Obviously, I've got my reactants on the top line and my products on the bottom line, which we don't normally do. We normally write an equation left to right, but just that was all I had room for. So we numbered our reactants 1, 2 and 3. Our butan-1-ol is reactant 1. Our sodium bromide is reactant 2, and our sulfuric acid is reactant 3. They can be in any order, but I just want to number where they appear in your method. So you can see here, step number 1 again is mixing the sodium bromide, which is our reactant 2, as we've numbered it, with butan-1-ol. So what I want you to see with this is that we're reacting together, or mixing together, 2 of our reactants. We're then told to place a reflux condenser in place above the flask and a still head above the condenser. So you can see here are 2 bits of apparatus, which you may or may not be familiar with. Here is your pear-shaped flask. And then here is our reflux condenser. So our pear-shaped flask contains our reactants at the minute, and our reflux condenser is essentially just a Liebig condenser but fitted vertically. And we would put water in at the bottom and water out at the top. We're then told in step number 2 that we put a still head above the reflux condenser. And what that does is it maintains what we call an open system. I would put a star by that term open system, and then put a star here at our still head. You can see there's a part of that still head that comes out and is open to the open air, so that allows what we call an open system. It allows the circulation of gas essentially, and it allows any gas products of this experiment to escape. Because they're not products that we want and could cause a buildup of pressure in our apparatus. So it allows essentially gases to move out. Then step number 3 is the addition of our third reactant. So our third reactant, if you look again at the overall equation, our third reactant is concentrated sulfuric acid. You can see from our apparatus that is added from a dropping funnel, and it's added dropwise because this reaction is highly exothermic. It gives out a lot of heat, and so it's important that we add dropwise, because if we don't and we add it too quickly, then the heat of the reaction and the rate of the reaction could cause the alcohol to become dehydrated. In other words, removing water from the molecule. I'll go back down to our little explanation here. So we're on step 3, adding concentrated sulfuric acid very slowly. So that's reactant number 3. So in step number 1, we mixed reactant 1 and 2 together, and we're adding now reactant 3. And remember, the concentrated sulfuric acid and the sodium bromide, those reactants are reacting together to give our hydrogen bromide in situ to then go on and react with the alcohol. Why we add it very slowly from a dropping funnel is to prevent dehydration of the alcohol. And evidence that has happened, the dehydration of the alcohol, which we don't want, would be some carbon seen as black flakes appearing in the reaction flask. So how that might come up in your exam, if you were ever asked on this method or a similar method, it might ask, why did black flakes appear? And you could say that concentrated sulfuric acid is a dehydrating agent. Or you could be asked how to prevent this from happening. You could say adding the concentrated sulfuric acid slowly or dropwise. Because if we add it too quickly, then sulfuric acid, because it's a dehydrating agent, it can remove water from the alcohol and leave us essentially with just carbon. So you may want to add, if you weren't overly familiar with that term dehydrating, you could say that essentially removes water from the molecule. And as you're told in that explanation there, that could lead to little flakes of carbon being produced if we rip water molecules away from the alcohol. And we also need to cool the contents, as it says here. We also need to cool the contents, and that you saw that in the practical video. How the pear-shaped flask can be placed in a beaker of cold water or even ice to cool the reaction down, because it's so exothermic and because this dehydration of the alcohol can take place. Step number 4 is to then remove the dropping funnel and add anti-bumping granules to the flask. And the purpose of the anti-bumping granules is to promote smooth boiling. That's a really common question. Why are anti-bumping granules added? And the key phrase is to promote smooth boiling. What does that mean? Well, these anti-bumping granules, they're little small tiny solids that essentially prevent the mixture from boiling too vigorously. It prevents them splashing up on the sides of the flask. Ultimately, we want these reactants to mix together, and so we want them to boil smoothly and not vigorously and not splashing all about the flask. So think about your kettle when it comes close to the boil and that water is splashing everywhere. That's not smooth boiling. Smooth boiling would be if the mixture is turning to a gas, it is boiling. But you can barely see any change, any movement of the liquid as such, because it's boiling so smoothly. So you may want to add a little note about that. The promotion of smooth boiling is essentially to prevent splashing up the sides of the flask, because we want the reactants to mix well together. So now that we've got all our reactants mixed together, what we want to do is to heat under reflux for about 30 minutes. So reflux is similar in some ways to distillation, but you can see here that our reflux condenser is fitted vertically. And you're told that in the explanation. So what we've got essentially is our reaction mixture. If it evaporates off, then it will condense in the reflux condenser and fall back down into the reaction mixture in the pear-shaped flask, allowing that reaction to continue. And the reason why we need to do it under reflux rather than just heating it, so we need to heat it because organic reactions are slow and so need to be heated. But also organic compounds are highly volatile. That means they evaporate easily. So we need to heat them to get this reaction going. But when we heat them, if we were to just heat them normally in an open flask, then actually our reactants would just evaporate off. And so therefore we wouldn't get a reaction happening. They would just escape into the air. And so what we do instead is we fit a reflux condenser so that we can heat it to get the reaction going. But when the reactants or the products evaporate, they will then condense. So reflux is about continual evaporation or boiling followed by condensation. So it says here there's continual evaporation and condensation without any loss of reactant or product. If you wanted to add to the top of your notes there, the SIA definition for reflux, which we've mentioned before, I think is on page 10 of your booklet, but you could write it here as well. The SIA definition for reflux is the repeated boiling and condensing of a reaction mixture. So you heat your reaction mixture under reflux for 30 minutes. So essentially after step 5, the reaction is done. So you may ask me, why are there 8 more steps? And that's a great point. But the rest of the 8 steps are about purification and extraction of the product from the reaction mixture. So you could draw a line in your notes after step 5 and just say essentially the reaction is done at this point. And then from step 6 onwards, it's all about the purification and extraction of the product from the reaction mixture. So separating and obtaining that product from the reaction mixture. And so yes, there are 8 more steps that we have to look at, and we'll start looking at them now. So when you're learning this, it might be worthwhile learning those first 5 steps together, learning how we actually prepare the product, and from here on in, we want to purify it and extract the product. So the first part of that purification and extraction step is to distill off the product until the upper organic layer has gone from the flask. So that's referring to the reaction mixture in the pear-shaped flask. The upper layer, upper organic layer, is our product. But you need to note at this point that some water will distill over with the organic liquid, which we don't really want, but it's very difficult to avoid. And that's because the boiling point of water is 100 degrees Celsius and the boiling point of 1 bromobutane is 102 degrees Celsius. So these are very, very close. So it's hard to distill over just the bromobutane because just before that comes over, the water impurity will come over as well. So when you collect it in a measuring cylinder or if you collect it in some other flask, you'll see 2 layers. Why do you see 2 layers? Well, we learned earlier on in the topic, one of our properties of halogenoalkanes is that they're insoluble in water. In other words, they don't mix well with water, and so when we've got an immiscible mixture of water and our product of 1 bromobutane, then they won't mix together and we'll see 2 layers. So again, that could be a question based on this practical. It could be why are 2 layers seen in the distillate, and that's because you've got some water impurity there and it does not mix with our halogenoalkane product. So the organic layer, you'll have an aqueous layer, which is your water that's distilled over, and your organic layer is mainly 1 bromobutane, but there'll be some impurities there as well. You'll have some water, which is a side product. You'll have some unreacted butan-1-ol, which is one of your reactants. You'll have sulfuric acid, which is also a reactant. And you'll also have some hydrogen bromide, which is an in situ reactant. So a lot of unreacted reactants here in our product. in our organic layer. So you can see here our apparatus set up for distillation. You can see that our condenser is here as well. It's very similar to the apparatus for reflux, but we've moved our still head down a wee bit, and the condenser is now in the normal position for distillation rather than reflux. So what will happen is our product at 102 degrees will evaporate off, pass into the condenser, condense, and be collected in the measuring cylinder. So our distillate was a mixture of two liquids that don't mix, and so what we use to separate a mixture that of two liquids that don't mix is a separating funnel. You may have seen this apparatus before with something like oil and water. So one of these layers is going to be our aqueous layer that mostly contains our water impurity or any other aqueous impurities, and then you'll have our organic layer, which is mostly our product. And deciding which layers which can be difficult if our liquids are both colourless, and so you can decide which is the organic layer in one of two ways. Either look up the density value of the halogenoalkane. If it's less dense than water, remember that the density of water is 1 gram per centimetre cubed, then it will be the top layer. If it is more dense than water, it will be the bottom layer. And if you were to do that, you would see that the density of 1-bromobutane is around 1.27 grams per centimetre cubed, and therefore it's more dense than water, and so therefore it's going to be the bottom layer. And the other way that you can decide if you didn't have access to density values or be able to look them up, you could add a small quantity of deionized water to the separating funnel, and the layer which increases in volume is the aqueous layer, because that water is going to add to the aqueous layer, and that will increase in size, and that will tell you which is the aqueous layer. And so the other layer will obviously be the organic layer. So you would place your distillate, which is a mixture of your two liquids, in a clean separating funnel and separate the organic layer. So essentially step number 7 is about removing the water. So we remove the water, we remove the aqueous layer, and then we can take our organic layer and purify it. So even though we have removed the water, there are other impurities that we mentioned in step number 6 that we need to remove now. So what we do is put our organic layer that we separated in step 7 into a clean separating funnel. And we add concentrated hydrochloric acid. Really, step 8 is about removing the unreacted butan-1-ol, and that is an impurity. So this removes the butan-1-ol impurity. It does this by converting the butan-1-ol to a more soluble ionic form, which will be more soluble in the aqueous layer than in the organic layer. So it will move to the aqueous layer, and then essentially you can use the separating funnel to separate those two layers. So essentially this step, adding the concentrated hydrochloric acid, is about moving the butan-1-ol impurity from the organic layer to the aqueous layer, because our desired product is in the organic layer, but we want to separate it away from the butan-1-ol. So if we get that into the aqueous layer, then we can run that off. So there's some details there about how you do that in the separating funnel. So it talks here about stopper the separating funnel, because you don't want to lose any of your product when you're mixing. And it says shake to mix. So you want it to thoroughly mix, so the concentrated hydrochloric acid mixes with the butan-1-ol and changes it to this more soluble ionic form. It says invert the separating funnel and open the tap of the separating funnel, and have a look up at the diagram above to see the tap, and that allows any gases that are produced in this reaction to be released to avoid the build-up of that gas pressure. Step number 9 is now about essentially, now that butan-1-ol is in the aqueous layer, and we want to remove it. So step number 9 is a bit like step number 7. So we do that by clamping the separating funnel, allowing the layers to separate. When you mix layers, when you have shaken it quite a lot, then it can take a wee while to separate, so let them separate. You need to remove the stopper, otherwise nothing will come out, and you need to allow that airflow in. And open the tap and allow the lower layer to run into the beaker. The lower layer will be your organic layer, again because of that higher density of your 1-bromobutane. And then it says close the tap when the junction of the two layers reaches the hole in the tap. You run off the upper aqueous layer into another beaker, and we can discard that because we don't want anything in the aqueous layer. We want our desired product, which is in the organic layer. Step number 10 is about removing another type of impurity that you have in your reaction mixture, and that's the acidic impurities. So let's have a think about what acidic impurities we have. Well, we have concentrated sulfuric acid. That was one of our initial reactants. And we have hydrogen bromide, which will have dissolved partly in the water to produce essentially hydrobromic acid. And then we also have hydrochloric acid from step 8, from trying to remove our butane 1, all impurities. So there's quite a few acidic impurities here, and so what we want to do is react that with something that will remove acidic impurities. And something that will do that is sodium hydrogen carbonate solution, or sometimes it is sodium carbonate solution. But both of those will react with acid to produce a salt, water and carbon dioxide. Again, we do this in a separating funnel because the products of this reaction will move into the aqueous layer, and then that can be removed. In this reaction, it is really important to invert the separating funnel and release the gas pressure by opening the tap from time to time, because we're producing carbon dioxide in this reaction. And so that will lead to a build-up of gas pressure in our separating funnel, so we've got to release that gas pressure. So again, our impurities will be removed and will be in the aqueous layer. And what we do is we separate as before, discarding the upper aqueous layer. And the bottom layer will be our organic layer, which contains our product, which we're getting closer and closer to. So at this stage of the experiment, our product will be cloudy because of the presence of water. That's partly produced in the reaction of our sodium hydrogen carbonate with our acidic impurities, as you can see in the equation here. So step number 11 is about removing the water. So essentially, with this purification process, we add one thing to remove an impurity. That produces another thing that we have to then remove. So that's why there are so many steps here. So step number 11 is about removing the water. So if we want to remove the water, then what we need to do is add a drying agent, and our drying agent in this case is anhydrous sodium sulfate. We can use something else like anhydrous calcium chloride. So we add that drying agent, we're given the example here, anhydrous sodium sulfate, to our product, to our organic layer that we've separated off from the separating funnel, and that's our 1-bromobutane. Add it in just small amounts, swirling after each addition until the 1-bromobutane is clear. We do that because when there's water in organic liquids, they can appear slightly cloudy, and therefore once the solution goes, or the liquid goes clear, that's a sign that we have removed all the water impurities. So we add our drying agent until it goes clear, and that's a sign that the water has been removed. What we then need to do is to remove that impurity, the impurity of any excess anhydrous sodium sulfate. And that's what we do in step number 12. The anhydrous sodium sulfate will have been a powder, and so we can remove it by decanting or filtering. Decanting is just when essentially you allow a solid to settle to the bottom of a liquid, and then you pour the liquid off into a clean beaker without disturbing the solid, essentially leaving the solid behind. So we can do that in this situation to remove our anhydrous sodium sulfate from our 1-bromobutane, or we can filter it to remove the solid. And then finally, we're on to our last step, and that is just to purify it finally by distilling off our product, our desired product. So we distill the 1-bromobutane and collect between a narrow range of boiling points. So remember that the boiling point of 1-bromobutane is 102 degrees C. And so we want to collect the distillate over a narrow range of temperature, usually 1 degree Celsius maximum either side of the boiling point, just to ensure that we are only collecting 1-bromobutane and not something like water, which has a boiling point of 100 degrees C. And we only want to collect that final product. Most of our impurities, all of our impurities should be removed by this stage, and we just want to remove any final ones from our product so that our product is completely pure. So that's a bit of a long process, a lot to take in there. So what I would suggest you do is to go back, and you may even want to watch the practical video again now that you have a better understanding of this process and why we do each step. But go back and read through your 13 steps. Remember, steps 1 to 5 of the process are making the 1-bromobutane. And then steps 6 to 13 are the purification and extraction step. So how we purify and extract our product. So this is the main method for preparing halogenoalkanes that you have to learn. We did say that this was method 1 of 6 methods of preparing halogenoalkanes, but you'll be glad to know that the rest of the methods of preparation only involve you learning an equation and some observations, and not a 13-step process. So we'll do that in our next video.